Welcome to the lecture series on soft computing in computer science. In this session, we are going to discuss about a new and innovative idea of combining two soft computing models. We have seen so far three soft computing model. One is artificial neural network, another one is fuzzy logic, and the last one is genetic algorithm. Here in this presentation, how two soft computing models, genetic algorithm as well as fuzzy logic, can be combined to solve certain engineering problems. Let me go into it. We all very well know that the fuzzy system consists of four major components: fuzzifier, inference engine, defuzzifier, and fuzzy knowledge base. All these four components are interconnected and are working together to produce the output. So this is we very well know about this idea during our past presentation. But the important point here is to note down is that fuzzy knowledge base. In almost all the case studies and applications that we have discussed so far, the fuzzy knowledge base has been intuitively designed. So what are the components of fuzzy knowledge base? The fuzzy knowledge base consists of two components. One is rule base, another one is database. Database is the one that consists of linguistic variables as well as membership function, whereas the rule base consists of fuzzy if then rule statement, right. So let us take this example, or let us revisit this example tipping problem. So given a problem statement, we need to identify the parameters, particularly the input and output, and for the input you need to divide the input into linguistics, and for the output you need to divide that into linguistics. For each linguistic you have to assign the membership function. Finally the rule base. So far we have discussed the rule base, only it is given by an expert like that, but we do not discuss any mechanism how this rule base is generated or what is the procedure to generate the rule base automatically. Once if you are ready with the database and the rule base, then it is very easier to understand the operating function of an inference engine and how the output has been derived from the system. So the main important point from this presentation is generation of database as well as the rule base. So in this presentation we are going to deal with how this database rule base are generated automatically and what is the support rendered by genetic algorithm to do so. So this is what we are going to see. So here I have taken an example of a classification problem. So far we have discussed about many case studies that involves the use of fuzzy systems. All are control related problems, starting from washing machine control, inverted pendulum, DC motor speed control, PID control, so and so on. So all these problems we have discussed how the fuzzy system has been used for control related problems. Even for control related problems as well as for the classification problem, two things are needed. What are the two things? Database as well as rule base, and this database and rule base forms the major part of the fuzzy system, because based on that rule base and database the fuzzy inference engine is executed and we are producing the result. So in case of classification problem, all these steps are needed. That is, we need to load the data set. In that, from the data set we need to choose the variables. This may be treated as set of input variable and this is an output variable, like that from the data set. These are all from the data set, and as usual for each input variable, if it is x1 it is entered into fuzzification, then it may be divided into low, medium, high, and x2 also low, medium, high, and x3 also low, medium, high. If you know the linguistics, you can divide that linguistic accordingly, otherwise you can simply go for low, medium, high. In case if you want to divide it into 3 linguistics, you can go for 5 linguistics, or you can go for 2 linguistics, or you can go for 7 linguistics. It depends on the complexity of the data that you are having. So this is the task fuzzification. Then after fuzzification the system enter into fuzzy inference engine. From the fuzzy inference engine, that is connected with knowledge base, the system is executed, and finally you got the class label as the output. Here there is no need for defaccification because we are having some mechanism here, and this mechanism will do it without defaccification, or we have some other procedures to derive the class label of the system in the rule itself, So this is what the way in which the fuzzy system can be deployed for performing a classifier model development. So in the fuzzy classifier model development, you have to understood that the rule based classifier. So yeah, what is a rule in general? A rule is consists of so many antecedents, that is if part, that tries to partition the input space into number of fuzzy regions, and consequence part, that consequence part will do the idea of generating the classifier in these regions. So these two things are needed, antecedents and consequence. So the fuzzy if then rules and membership functions are the major issues that you should understand, that fuzzy if then rules and membership functions are the major issues while designing a fuzzy classifier model. We have two approaches, one is human expert based approach, another one is data driven based approach. When you take the case of human expert approach, whenever if the number of variables get increased, the number of rules is also getting increased exponentially. So it is very difficult for the human expert to define the complete set of rules for a good system performance. So human expert system is failing this part. What about data driven approaches? If you take the case of data driven approach, you can face that experience that this data driven approach is very weak in self learning as well as determining the number of necessary fuzzy if then rules. So that you should take care of it. So when you are going to design a fuzzy classifier model, you have two options. One is you can go for expert system based approach, that means human experts based approach, or you can go for what purpose these two things are needed? In order to generate if then rules and membership function. For these other two purposes we need to do. So the problem statement is clearly stated that there are two ways of designing a fuzzy expert system for performing a data classification task. One is human expert, another one is data driven approach. And in both the cases, the tasks that are defined as a search and optimization task. So what is this search and optimization task is doing? It is going to search the rule set as well as MF and try to optimize this rule set and MF. So first it will going to search and then it will try to optimize. So it will try to explore the possible rule set combinations and possible membership function shape, size, as many as possible linguistics that are needed, and then it tries to optimize it, which is essentially needed based on the classification performance. So this is what the problem statement is all about when you want to design a fuzzy expert system for a data classifier model. So when you want to design a data classifier model using fuzzy logic, the rules set and membership function, you cannot get it from the expert, because for the plenty of data sets, for the unexplored application domains, the data sets, the experts are not available. So we cannot rely on the expert to design the rule set and membership function, or we cannot rely on our intuitive approach of simply dividing the input variable into some linguistics and assigning the range of the variable, this range to this range is low, this range to this range is high, like that, allowing some sort of uncertainty or overlapping between the variables. So those intuitive approaches are also failing, because it is all did based on our own experience. So what one can do is you can go for the another method called data driven approach. Sometimes these data driven approaches is also failing because it completely rely on data and it doesn't have any flexibility for the unknown data that can be generated in the near future. So it works only for the past data, but for the present as well as for the future data, it may have any disturbances in the data, or if any new unexplored data or situation may come, this problem is getting failed. So what one can do is you can design this kind of problem, that is designing a data classifier model using fuzzy logic as a search and optimization problem where the rule set and membership function can be generated by means of search and optimization task. Let us see how these rule set and membership functions can be generated using genetic algorithm. So first you need to define this problem as search problem in high dimensional space where each point represents a rule set, membership function and a corresponding system behavior. First it is viewed as a kind of search problem in high dimensional space, right. Now if you give some performance criteria to check whether the system meets the requirement or not, then you need to check the performance of the system that forms a hypersurface. So developing the optimal fuzzy system is equivalent to finding the optimal location of this hyperspace. So for this kind of problem statement, many evolutionary algorithms, particularly genetic algorithms, makes a suitable candidate for fuzzy classifier design. So apart from the human expert approach as well as the data driven approach, here our task or here our way is looking at the problem as a search problem in the high dimensional space. And what we are looking for and what we are searching for, we are searching for the rule set, we are searching for the membership function and for the system behavior when you combinedly trigger the rule set for the membership function. So these three things we are treating as a search problem in the high dimensional space. So the performance of the entire system is depending on the system performance in the hypersurface. So it means that when you want to develop an optimal fuzzy system, it is directly equal to identifying the optimal location in that hypersurface. So it means that the problem is entirely and the problem is purely an optimization problem where the genetic algorithm came into picture to solve such kind of problems, particularly designing the classifier model for fuzzy classification. How to solve? You all very well know about from our past presentation the general steps of genetic algorithm. What are the general steps? Problem representation, population initialization, evaluation of fitness value, application of genetic operators and reproduction, crossover and mutation. So these are the things that you can follow and these genetic operators have been repeatedly applied in order to obtain the best fitness value. There you need to stop the process. This is the first step, this is the one time step and this is also one time step, these two are one time step and this is the repeated step and this is also repeated step, right. Finally you got the answer without compromising the any other constraints or any other conditions imposed on the problems. So in order to do so, that means we have only data and we are going to apply genetic algorithm. The first step is problem representation. So what is the problem? The problem of generating membership function and rule set is our problem, right. So the problem representation starts by representing the membership function. For simplicity, we have taken 3MF for any variable that are present in the data set and for low and 3MF membership function is low, medium, high and for low we have taken half trapezoidal and for high we have taken the half trapezoidal and for medium we have taken the triangular and it is shown in this figure like this. And if you could see that we have 9 cutting points, this is P1 point, this is P2 and this is P, this is 1MF and it is treated as low. And we have another things P4, P5, P6 and this is treated as another MF and this is treated as medium. And this P7, P8, P9 and this is treated as another MF and it is high. So like this the optimal points needed to represent a membership function is designed. Please remember here we fixed our scenario for each variable that has been chosen from the data set. It has to be divided into 3 linguistics and for each linguistics 3 membership function is assigned trapezoidal, triangular and so this is in case if you want to use a binary GA or in general it is a simple GA, general GA, each fuzzy set is represented by a 2-bit stub string. An additional 2-bit is used to represent the output class. So if you have maximum of n rules are represented in the genetic class, so you need additional bit called rule selection bit. So these are all the things that you can use it for rule generation. So having used this representation strategy with the help of genetic algorithm, then the sample chromosome is like this. See, for each input variable we have 2 bit substring. So that means 0 0 we avoid this, don't care. 0 1 the low one, 1 0 it is medium, 1 1 high for each IP, for each IP. Likewise for each OP, if you obtain 0 0 we want to omit that, and 0 1 and 1 0 and 1 1 we have to consider that, and this RS rule selection, and it will take either 0 or 1. If it is 0 we have to avoid that rule, if it is 1 we have to select that rule. So this is for the representation strategy, and this representation strategy for rules can start from rule 1 to rule NR. NR is the maximum number of rules that we need to generate. Correspondingly, coming to the membership function, this is M of 1, M of 2, M of n for the input variable 1. Likewise for the input variable 2 and for input variable n. And these point represents the cutoff points P1, P2, P3. See, P1, P2, P3. That's why I represent as M of 1, M of 2, M of n. In case if you have P1, P3 variable, this is P1, P2, P3. This is for the half trapezoidal function, this is for triangular function, this is for another half trapezoidal function for every variable. You can go for like this for n number of input variable. So this is for one input, this is trapezoidal, this is another one, this is another, like that. So this is the representation strategy that you can follow it for representing the rules as well as membership function. Now the another important parameter is fitness function, how the fitness function is designed. See, what is our objective? Our objective is to classify as many as possible data as possible. So the fitness function that can be generated as minimize f equal to capital S minus CC. What is capital S? Capital S is total number of samples. What is CC? CC is number of correctly classified samples, NR is maximum number of rules, and K is a constant. So the fitness is the reciprocal of this objective function value. So our objective is to maximize the number of classified data as well as minimize the number of rules. If you minimize the number of rules as minimum as possible, then we can say that the system is very compact and easy to handle. So that's why in that idea only the fitness function is generated. So I think once again recollect you the idea. Our objective is to maximize the correctly classified data. So the maximize the correctly classified data is treated in the form of an error. So it means that it has to be minimized, the error is minimized. So this S minus CC is error, and this is minimize the number of rules. So overall the problem is, but if you look at this, the problem is here having two contradictory objectives. One is maximize the correctly classified class, another is minimize the number of errors. So these two contradictory objectives can be made into a single objective by means of maximize the number of classified data into CC. Instead of maximizing the CC, you are minimizing the error. What is error? Error is nothing but maximum number of samples minus CC. In that idea, we are devising the fitness function. Now these two things is ready. What is ready? Representation ready. So based on the representation, what you can do? You can generate the population, and the fitness function is ready. So for each population that you have generated, you can evaluate the fitness function to test the, then you can apply the genetic operators, based on that you can see the results. So let me explain the idea of this execution of this algorithm with iris, wine, breast cancer, and DCP dump data. DCP dump data is a data which is meant for detecting intrusions. The parameter setting is population size is 30, crossover probability, mutation probability, and tournament size. So this thing you need to remember while you are setting the genetic algorithm. Of course, this thing will be seen in detail in MATLAB practical session. Right now you please understand that the concept of designing the fuzzy classifier model using genetic algorithm, that is GFS, genetic fuzzy classification system, has been illustrated using iris data, wine data, breast cancer data, and DCP dump data. So what are the objective? Our objective is to receive membership function as well as rule set. Initially we have only the data alone we have. What is the output? Membership function and rule sets are output. All are followed by correctly classified data. So we need to know that, right, how many samples have been classified. So that is the final outcome. What are the control parameters as far as the genetic algorithm is concerned? Population size, crossover probability, mutation probability, tournament size. These are the control parameters for this simple genetic algorithm. So this simple genetic algorithm is trying to use the binary coded string. If you look at it, the representation, all are binary numbers, zeros and ones. If you look at it, all are zeros and ones, and these zeros and ones represents the binary numbers, and based on the principle of genetic algorithm, this binary number can to be converted into the equivalent real values, and then the system is evaluated. Classification of iris data. This iris data is very commonly studied data, where you can find this data in UCI machine learning repository, and this data have 4 input variable and 1 output variable. The output variable can take 3 kinds of flowers. 1 means for setosa, 2 means for versicolor, 3 means for virginica. So these are the 3 classic labels that you can find from the iris flower data, and there are 4 variables: sepal length, sepal width, petal length, petal width, 4 input variables. So we have 4 input variables, and these 4 input variables has been taken for this. So once this data is supplied, so you need to take the minimum and the maximum. Why is it so? Why we need to take the minimum and maximum value? Because the sepal length is the variable, and this sepal length variable has to be divided into low, medium, high, right. So low starts with 4 and high ends with 8. Between these you need to divide this variable. For low you need to divide design a boundary, for medium you need to design a boundary, for high also you need to design a boundary, but all these 3 boundaries should be well within this overall boundary. And if you do this task, this is called falsification task. So this is wow, we need to understand that. So the population initialization is C, the minimum value and the maximum value. Sepal length 4 is the minimum value and 8 is the maximum value, and all these other values are initialized based on the value that you have got while representing the membership function. And the rule set is sepal length, sepal width, petal width, C 2 1. So what is this 2 represents? 2 1 2 2 1. See here 2 is sepal length, so this is sepal width, petal width and a class label, right. This is 2, right. So this 2 means what is the range of the variable it is available, accordingly the rule set class has been taken. So sepal length 2, for sepal length you have 1 2 3. So 2 means it is medium, 1 means it is low, 3 means high. So accordingly we can represent the entire system. So the fitness function evaluation has been taken. So the fitness function evaluation has been taken is f of s minus cc knr. So what is the maximum number of data? 150 amount is the number of data. So for a particular generation, if 28 is the data that has been generated and the maximum number of rules is 6, so accordingly the value has been collected 152, the value has been generated and collected. So what you have, how the fitness is calculated? It is the reciprocal of k by f. So accordingly the fitness has been selected. So here an eraser is there. So I will erase this thing so that you can know very well about how this fitness has been generated. See, the minimum fitness f of s equal to s, s is 150. How many number of data is there? 150 data is there. At the particular form, the data generated is 28, the rule is 60. So fitness is calculated, and then the fitness is calculated like this. So this is the evaluation of objective function, and this is the fitness value. So like this you calculate it for every variable that you use available in the data. So if you do so, you got the final membership function. See 127, 127 maybe it is the range of 127 petal length here, petal length. So the obtained membership function it is displayed for simplicity. This is petal length 127. After that 127, here 1 is there, here P1, this is P2, this is P3. So what is this point? P1 is 0, P2 is 0, what is P3? P3 is 2.5. So accordingly that diagram has been plotted. And what is another membership function, that is P4, P5, P6. So P4 is 2, P5 is 3 and P6 here, right, something like 5.3. So like this, this is P4, P like this form. And what about the third one? Here it has been started. Yes. Here P7, P8, P9. What is P7? P7 is something like 4.3 and P8 is 0, 0. So this is what we have obtained for petal length. I hope you understand the idea. So we have some set of points and these set of points are generated over the values and it is generated according to the points. So what are the rules that has been obtained? You can understand the rules from this 2, 1, 2. If sepal length is, what is 2 represents? 2 represents medium. So if sepal length is low and petal length is low and petal width is low, then it is iris versicolor. If sepal length is low and petal length is medium, so it means that sepal length is the first variable for which low means 1. Here petal length is 1 and here also 1. If 3 are 3, 1, then the class is 2, like that. So here you can understood from this, like that. So 2 represents medium, 1 represents high, like that, right. So we have generated this. So now what we got? We have not generated, we have not initialized the membership function, we have not added the membership shape, we have not arrived at the rules. The genetic algorithm is finding the rule set. So the finding of the rule set has been tuned every phases of iteration and finally it get saturated at one point. At this point you have to stop and you have to display the membership function and the rule set. Similarly, for the intrusion detection, the variables are source IP, destination IP, source port number, destination port number, protocol used, and the intrusion detection after applying genetic. This is the rule set that we have got. This is the rule set. If higher value protocol is being used, then it is normal connection, whatever may be the source and the destination port. If a medium value connection is like that, we got for the DCBTM data. For breast cancer data, we got this answer, the genetic algorithm. If you could see that the performance of for over the various data, you can find that the generation for, since it is a smaller number of amount of data, you can find that 300 is the maximum generation and the population size if we have been tested to 30 for all the cases, crossover rate and everything is that. You can find that with the 3 rules you can do the iris data classification, but for wine we need 60 rules. For 3 rules it obtained 97 classification, 97.3%. For 60 rules it obtains a 90 pointer. So for 2 rules for DCB data we need 95, we obtained a 95.9. So if you could see that still there are some possibilities of improvement or is there with the kind of genetic algorithm. See, this genetic algorithm is a simple genetic algorithm. With the help of this simple genetic algorithm we obtained this results. So what is the optimal rule set? Obtained by this is a for iris data, this is the optimal rule set. If sepal length is high and petal width is low, so this is the optimal number of rule set and this is the, likewise you can define the optimal number of rule set for other cases. So what we have understood from this presentation is with only the data that we are needed to classify using fuzzy logic, the fuzzy logic can classify any data provided it has to be supplied with membership function and rule set. In general, the membership function rule set cannot be supplied for a data. So in order to generate or in order to find out the optimal as well as the suitable membership function as well as the rule set from the data, the problem is defined as a optimization problem where which we can generate the rule set and membership function, and then the rule set and membership function can be utilized in the fuzzy expert system to fire the system, and that system is fired in order to predict the class label of the data, and the class label of the data has been accounted and we have to report how much percentage of the accuracy the system has been obtained. So this is the way in which you can utilize the genetic algorithm for designing the fuzzy system. In all our previous case studies, what we have discussed is, we have discussed how to design the fuzzy system alone by giving out the membership function as well as the rule set. Someone has given you the membership function and rule set and your task is to design the fuzzy expert system. But here the case is you are provided only with the data. From the data, how we are going to generate the rule set and membership function, and how the generated membership function will be utilized for designing the fuzzy expert system or for performing the classification task. So with this we can close the idea of designing the fuzzy expert system using the genetic algorithm. Maybe in the subsequent presentation we will discuss about how the performance of, see if you look at this, the performance is 97, 90, 95 So it means that still improvement is possible. So how that improvement can be made possible by means of some additional algorithms, and how the data set has been improved to bring out the good idea, and how new innovative idea has been brought into the pictures and everything, right? Thank you.